of resources will be efficient, and production won't depend on the allocation of property rights. Okay, so that's a proposition which was very surprising to economists in the 60s when Coase first devised it. It now seems a lot more natural. I want to go ahead and sort of apply this theorem to our beekeeping example. You can sort of see how it works. Yeah, but the basic story is this. The basic motivation is this. If you have two private parties, there's an externality where it would be to the mutual benefit of both parties if the externality were removed, and that's sort of the definition of externality, then they ought to be able to work something out. If they can work something out, then production will be efficient. There might be some side payments involved, and that's why property rights might matter, or might not matter to the Okay, so let's talk about the possible Coasean solution to the bee and apple problem that we've been working with. So we thought about a couple different ways of tackling this problem. One way we thought about solving the problem of the externality was just a buyout. We could have the honeykeeper buy the apple orchard, have an integrated operation. What was formerly an externality is now an internality, I guess. Is now internal to the firm, and so production is efficient. That works. That's one solution. A second solution involves the story of Pagovian taxation, and that works too in principle. In practice, it might be difficult to administer sometimes. A third possible solution here is going to be a Coasean solution, so that's what we're going to talk about next. So here's how it would work. The idea is the apple, the apple orchard proposing this thing. So the apple grower has this orchard next door. The apple grower knows that production will be higher if there are more bees, and so he simply walks next door and says, hey, if you'll add more hives to your operation, I'll help pay for it. And so the proposed contract here is to say, well, look, for each additional, every unit of bees in excess of BP, for each additional unit of bees you keep, I'll subsidize the cost for you. And so this is a case where the government's not involved in a way that the apple grower is sort of providing a Pagovian subsidy, if you like. Anyway, so there's a contract between a private contract between these parties that involves the apple grower helping to subsidize bee production. So we need to think about the payment here. The payment has to be big enough to induce the beekeeper to actually sign the contract, so we need to check that. And so the requirement we're going to need to solve in designing this contract is that the beekeeper's profit is going to have to be at least as large in the presence of the contract as they would be if the contract wasn't signed at all. So that's the basic problem we're going to try to solve with this Coasean problem. Okay, so let me go ahead and try to write down this problem facing the apple grower. And the way to think about this is that the apple grower is trying to devise the optimal contract to present to the beekeeper. So that's the way I like to think about this problem. So a contract to design. And so let me remind you of a couple things. First of all, we have a private level of provision. This is which is what happens before the contract is in place. That involves a quantity of output, which is pH over 4C, this quantity squared. Now, given this quantity, what we're going to have is the problem of contract design. What we're going to want the orchard owner to do is to design a contract by choosing the quantity of bees to ask the beekeeper to keep and a payment per hive of Q. He's going to do this so as to maximize revenues from his apple orchard. So he's going to get PA for each unit of apples. The quantity of apples he gets, remember, is just equal to the square root of B. So this is his apple revenue. Now, previously, we didn't have the apple grower facing any costs, but now he does face a cost. What's the cost he's going to face? Yes, the subsidies he's paying to the cost sharing he's doing with the beekeeper. So he's going to have to pay to the beekeeper a quantity Q times the number of bees that he asks the beekeeper to keep in excess of BP. So remember, he's only paying for the bees in excess of what the beekeeper is already keeping. Yes, again. This is BP. No, well, in nature, this is just the thing he's choosing right now. So the contract's going to say, hey, have this many hives on your property, and I'm going to pay you for each hive, above what you had before. Yeah.
So is the profits in the second bullet point, is that the beekeeper's profits?
Oh, yeah, well, that's good. So that's going to be the beekeeper's profits, right? So this is a private contract. The apple grower can't go over there and force the beekeeper to sign this thing. So we're going to need to make sure when we design the contract that both parties benefit. Okay. So there's going to be a constraint that the orchard, that the apple guy faces. He's going to have to be sure that the profits for the beekeeper, just what we were saying, the profits for the beekeeper are at least as large as they were before. Profits before were pH times the square root of BP, where BP is this quantity, and minus C times BP. So this is profits without contract. And the actual contract is going to have to get profits which are at least as large as these. The profits in this case will be pH times the square root of B plus Q minus C, because it gets a subsidy here, times B minus Q times BP. So this is the revenue we get from the honey production. This is the payments that the beekeeper gets from producing bee. We net out the payments that he would have received, that he doesn't receive for his existing stock of hives, BP. Yes?
Where's the square root of BP come from in the first left?
Yeah, so I was worried about that too. Let's see. The concern is, we have, that's a good question, thank you. So what we have is H equal to the fourth root of B times the square root of A. But I've gone ahead and done the trick of substituting in the square root of B here, which gives me back square root of B for the total honey production. Okay, there's a problem there? Yeah. He benefits from every unit of B. Yeah, he's going to pay. The set of this contract is he's only going to pay for what the beekeeper wouldn't keep on his own. On her own. I'm subtracting off the. Yeah. So this is a good question. This is all equal to minus CB plus Q times B minus BP. If you prefer, maybe that's a clear way to write it. Okay. All right. Okay, let's move ahead here. Okay, so this is the problem. We've got an inequality here, so I'm going to use a Kuhn-Tucker approach to solving this maximization problem. Um, so the Kuhn-Tucker version of this is going to look like this. We'll maximize by choice of B and Q still. Same thing, P A times the square root of B minus Q times B minus BP plus, and here's where the constraint comes from. So the Lagrange multiplier lambda times pH square root of B plus Q minus C B minus Q BP minus, I'm just going to write this way, pi sub P with the private profits previously earned by the beekeeper. Okay, so that's the Kuhn-Tucker version of the problem. We get two first order conditions from this. First of all, let's think about choosing Q. So maximizing with respect to Q, we get a B minus BP plus lambda times B minus BP, and that's it.
Negative B minus BP.
Oh, I see. Yeah, you're right. Thank you. I'm sorry. So who said that? You're Nick. You got that? Okay. Right. So here's the expression we got from Q. Notice something that happens quite beautifully and immediately from this. As long as B is greater than BP, this quantity is positive. We divide this thing. So this implies one of two things: either B is equal to BP, or lambda is equal to 1. Yeah.
So if you're a pi P, then have a Q become as well.
Yeah. I don't have a Q in there. The pi P doesn't involve Q. And regardless, the BP is just pH over 4C. So there's no choice variables involved in that. So okay, so now let's take the other first order condition. That's how many beehives we want to write into the contract. So how many bees should this guy keep? And so the first order condition here, we get a 1/2 times PA over the square root of B minus Q plus lambda times pH over 2 root B plus Q minus C, and that's it. It's going to have to be equal to 0 at the optimum. All right. Okay, and so solving this thing for B, let's see, let's collect, well, first of all observe that lambda is equal to 1. Either B is equal to BP, in which case it's efficient already, or else lambda is equal to 1. So let's take lambda equal to 1 and collect in terms here. We're going to have then 1/2 times PA plus pH divided by root B, and that's going to be minus Q, but plus Q, minus C, which implies that B here is equal to PA plus pH all over 2C, quantity squared. And recall this is equal to the optimal level of production. Okay, so this device of writing a private contract that gives a marginal payment for each additional beehive over the level of BP gives us an efficient level of bees. That's the first thing that was promised to us by the Coase theorem. And there's nothing in here. What were property? I should ask this before. What are property rights here? What do we have that look like a property right? Any thoughts? Yeah.
It's defined who owns the bee operation and who owns the apple.
It depends on who owns the bee and apple operation. In this case, it implies that the beekeeper has, because he has a property right to produce bees, and by acting strictly on her own, she can go through the level of BP like this and earn profits of pi p. So she has a property right to pi p in this case. But notice that this level of B that gets chosen now doesn't depend on pi p. So we got efficient levels of production. It doesn't depend on the allocation of property rights. Yeah. We can solve for Q. Actually, let's do that next. So we've got a level of efficient production for B. The question now, which is quite correct, is how much Q is actually going to get paid. Now, there's actually lots of things that could solve. There's lots of different levels of Q that could solve this. The question here is going to be the larger the transfer of Q, the better off is the honey grower. And so there are levels of Q which are larger than some minimum level. Those will also solve this problem. So let's find the smallest value of Q that solves this problem. So to do that, what we want to do is to find exactly the level of Q that satisfies this inequality with equality. So it's the smallest payment that the apple grower can make to the beekeeper to make her as well off as she was by producing privately. So is that clear? So we figured out the optimal level of production here. We need to have Q to make it work. We need to pay Q in order to make lambda equal to 1. So now we need to figure out the minimum Q necessary to make the beekeeper as well off as she would be otherwise. Okay, I'm almost out of time, so I'm going to put a box around this. And what we want to do is substitute a B star in here. Let me call it out separately. So we want to find the thing that makes this pH times root of BP, this still shows up, minus C times BP. So all this stuff is unchanged. This has to be less than or equal to pH times the square root of B star that we just found we had there. And we'll have plus Q minus C times B star minus Q BP. And there's some minimum level of Q, called Q underbar, that solves this thing with equality. I'll tell you what it is. This implies that the minimum payment Q bar is going to be equal to a quantity C minus pH times the square root of B star minus the square root of BP. BH just times that whole thing, divided by B star minus BP. So this is the minimum level of payment, a side payment, if you will, that the beekeeper needs to make to induce the apple grower needs to make to the beekeeper to induce an efficient level of production of bees. All right, so that's Coase. I want to just point to a couple things. We've got efficient production. I already emphasized that. the efficient level of production B star did not depend on property rights, but something else does. This transfer Q underbar does depend on property rights, as measured by this BP. This BP is a measure of how well off the honey grower is in absence of a deal, and so we can think of this as reflecting the presence of property rights. So production is efficient, there's a compensating transfer that depends on property rights, and that solves the externality. Okay, thanks. See you for a second.